Okay, so we have Ridhima next, who would be talking about upper limits on the 21 centimeter power spectrum from MWA. Ridhima, this is 12 plus 3 minutes, so I'll let you know when we are at the 12-minute mark.
Thank you. Hello everyone, my name is Ridhima and today I'm going to talk on the latest results that we obtained on the 21 centimeter power spectrum using MWA, and I'm presenting this work on behalf of MWA collaboration. Okay. Sorry, I was having an issue in just going through my slide. So just to start off, I'm just going to give an overview of the MWA observation setup. So here is just a picture of the MWA dipole. And I think probably in the crowd, I'm not sure, there's various people. So I'm just going to state that MWA was built in different stages. And the first stage was 128 antennas, which was randomly arranged. And then it was a different configuration where we had 128 antennas, but two of them, we arranged them in hexagonal structure so that we could get a bit of sensitivity and also take advantage of redundancy, where we could apply redundant baseline, which is a good thing as well. And it didn't prove to be that useful for MWA, for ER. But in this work, we use observation from both configuration, which means that we had data from 2013 to 2024, which makes about 157 hours of data. And we had about 19,000 of observation, which was about 2 minutes each. And we also included all the pointings, which was from pointing -3, -2, -1, 0, 1, 2, and 3. And here is listed the altitude and azimuth. And from previous studies, MDiv observed at 3 different fields, but from the previous literature and work that has been done on the ER field, we found that ER0 is the best field because it doesn't contain bright sources or extended sources such as Phonax A and Hydra A. So we chose for this work in particular ER0. Also, we have some of a contamination from the galactic center, but we try to get rid of them using our strategy. So moving on, I will just show here a timeline of the power spectrum limit that has been done from 2016, where we started at around redshift 12.2, and we got a limit of 2.5 to the power of -7 millikelvin square. And then after a few years, we have Barry, which gave a good limit, which was able by just trying to improve systematics and using better RFI flaggers, which were previously we were not able to detect signal which was coming from plane, but by using new software, flagging software, we were able to go lower to our limit by removing bad data to 10 power -3. And then we start improving on calibration strategies as well as choosing the best ER field. We were able to go to 10 to the 3 itself, but from 3.9 to 1.8. And using the 3 last years, we found that MWA observation for ER is more sensitive at redshift 6.5 to 7. So for this work, we'll be focusing at this particular redshift, and we also extract our upper limits at this redshift itself. So moving on, so what we learn is the 2 main dominant systematics or challenges, I would say, for 21 centimeter is calibration. So calibration, we have errors because we have uncertainties in our sky model. We try to model as much like point sources and extragalactic, but we're still missing diffuse emission. And of course, we have extended sources like Phonax A and so on, which we are like not very good in modeling. But this we could escape for ER0 because Phonax A is not in the field of view. But and also we have uncertainties in the beam model. And secondly, systematic, which MWA, although it's located like in a nice environment, we found that we are still dominated by RFI, which is buried under thermal noise, and they are not sensitive to our current flagging like whatever tools we have, they are not sensitive to them. So we try to build our pipeline based on all the lessons that we learn and trying to make sure that we don't include doubtful or anomalies in our observation. So we have been very careful while designing the software. So at each of these intermediate steps that you can see, so these are the steps that we took, and at each of this intermediate step, we make sure we do our mitigation analysis, try to detect anomalies by looking at the various distribution and also extracting various data quality metrics to make sure we are discarding any bad antennas, timestamp, frequency, as well as a whole observation if we found them not good enough. So to start off, we start our data. Like I said, we had 657 hours. And those boxes which are highlighted in blue here are the data processing and power spectrum analysis. And then the one which is highlighted, which is highlighted in pink are the validation steps that we took to make sure our data are good at the levels that we expect. So here with Burley, we did like just processing. We process the data and average them to 2 seconds and 40 kilohertz. And then we apply a sense. But before applying sense, after doing the averaging, we make sure that we discard all the data, all the data quality issues that were reported by the monitor and control system, as well as we did some analysis on the autocorrelation and derive some statistic, which we found if there's any antenna bad, we just get rid of them. And after that, we again did some analysis on the autocorrelation to make sure in terms of time, if all the time are working properly. And then we did direction independent calibration using a new software called Hyperdrive, which is an improvement over the calibration software, which was used previously in the previous derivation of the upper limit. And at the same time, we also use Hyperdrive itself. There's foreground subtraction by just doing a direct subtraction of the source models that we use for calibration. But on top of that, we found that there is source offset. So when we do a direct foreground subtraction in the visibility plane, we found that some sources are under subtracted and some are over subtracted. And the reason being because of the ionosphere, the sources tend to offset a little bit. So we apply the offset correction before doing the foreground subtraction on the brightest 1,000 sources. The reason we use the brightest 1,000 sources because they are accurate for the bright one, and the phase offset are not found to be the uncertainties associated to phase when the sources are faint or large enough. So instead of improving our result, it kind of deteriorates our result. So that's the reason we choose only the 1,000 brightest sources. And after getting our calibrated visibility, both subtracted and unsubtracted, we derive some data quality metrics on them. And based on the distribution, we get rid of some anomalies, some outliers. And then whatever were left, which was about 268 hours, we fed it to the power spectrum estimator, which is CHIPS. And after getting the result, we did some validation, which I'm going to talk about later down the presentation. So here's I'm just showing an example of how our foreground subtraction improved from before and now. So here to the right, you can see this is an Stokes XX before ionospheric correction. So there was no ionospheric correction done into that. This is just a subtracted image, just taking the visibility and subtracting it, the model visibility, subtracting it from the data. And in the middle panel is after doing the ionospheric correction, which means we correct for the phase offset. And to my left here, you can see there is that's a difference, and you can see the difference shows there were so many sources that were and the subtracted, which after doing the phase correction, it's much better now. So that's the improvement from the last pipelines that we had. And secondly, I'm just going to present the matrix that we use. This is some of them, which we derive from the image, which were both from foreground subtracted and foreground unsubtracted, which means that just calibrated visibility. So we get some of this matrix from the image, and also we use matrix from the delay transform visibilities, which is just taking the Fourier transform of each visibility across baseline and frequency, for each baseline across frequency, and doing some matrix around there to look if we could see any kind of systematics in here, and it's much easier to see it in the Fourier space. Now I'm just showing how many observations were discarded from each of this data quality matrix. Here I'm just presenting, I combine the data matrix in one of like quantities which we could read. So there's another thing which I need to mention is we had previously I mentioned we observe at different pointings. So we also saw that from the different matrix that pointing -3 is actually dominated by the galactic center. So we still have contamination from the galactic center, even though it is like at the corner of the second side lobe of MWA primary beam. So that's the reason we found that it's not good enough for us to include it in our observation. So we get rid of pointing -3 observation and just use pointing -1 and -2. And also based on the number of observations that get discarded by our matrix mitigation strategy, we found that the main culprit is RFI. So the since total occupancy are also RFI, but it's a different RFI flagger, whereas AOI flagger is 885. So since works in a way that it actually works per baseline, so it is more sensitive to RFIs that are buried under thermal noise. So it allows us to get this RFI out, identify them, and get rid. But in our analysis, we don't get rid of that particular RFI, but instead we get rid of the whole observation if we found that the occupancy is greater than 25%. Moving on from this remaining 268 hours, we form 2D power spectra. So here's a result of the 2D power spectrum at 3 different redshifts. And using this 2D power spectra, in order to construct the 1D power spectra, we select the best region in the EOR window and average over K perpendicular. So here the regions that I have highlighted in blue is a region that we chose, and we found that it is a region that has less contamination, and therefore we average over the K perpendicular. And averaging through them, we get, so I'm just showing here for redshift 6.5. This is a power spectrum, and the one which is in orange is a power spectra with a 2 sigma error on it. And we found that this is a power upper limit that we found here. It's much lower than what we previously found at that point. Here, sorry, it's here. At redshift 6.5, so it's about 30.2 millikelvin square, which is 1 order of magnitude lower than what we previously found in 2020, and around the same K mode. And for redshift 6.8 and 7.0 as well, it's lower. So it's about 21.3 to the square millikelvin square. And at redshift 7.0, it's 39.1 to the square millikelvin square. And we found that the best result is along east-west polarization, because it works best for MW observation. And having a look at where we are currently standing. So at this particular redshift, we don't have any other instrument that work. So we have to compare it with MWA itself. And when we compare it with MWA itself, this is where we are lying, which is, of course, a good improvement over existing result. But comparing with other instrument, this is 7, we have a result at 7.0. Unfortunately, we don't have any other instruments that works at have upper limits at this particular redshift, but we have Hera, which is a bit lower, which is 7.8, which is here in green. So the green arrows is showing Hera upper limit. And as you can see, we don't do better than Hera. Hera does best, but still it's at a different redshift. So we can say that at 7.0, we're still doing better. And of course, we have to validate our result to make sure whatever we are getting, we are not including any bias in our pipeline. So there's two ways we did our validation. The first one is just verifying it through an end-to-end simulation using Warden. And here is a plot which shows that we use the same, so as foreground, we use extragalactic, the same lobes catalog, and try to include all the instruments that we could get, instrument systematics and stuff. And we found that we needed to apply a normalization factor, which Warden was able to derive it for us, which were about 2.6 as normalization factor, which we applied. And we found also that there's no signal loss as such in our pipeline. So we are good to go. And the second validation we did is through FHD, which is a completely independent pipeline. And we just use a subset of 300 observation and fed it to FHD and also to our CHIPS pipeline, hyperdrive CHIPS pipeline. And then we compared the both output from them. The purple line shows the output from our pipeline, and the brown line shows the output from FHD pipeline. At lower K, we see that there is kind of consistency at almost all the redshift, whereas at high K, we see that you can see that our pipeline doesn't do good, doesn't work that much. And one of the reasons we found that it's because the averaging is done, our averaging, we anticipate that because we do averaging at 80 kilohertz, whereas FHD does averaging of the visibility at 160 kilohertz, which tends to decrease those harmonics that we saw that in the 2D power spectra. Therefore, that's why the power around the harmonics decreases at large K, whereas for us, it's still there. And they do this averaging, it's not a straightforward averaging because they go in a different space and while we stay in the visibility space itself. That said, now when we have already validated our result, we did some cosmological inference with the help of Yusha.
Sorry to interrupt. Yeah, we are at time, so could you quickly sum up?
Yeah, sure. So we found that we didn't, of course, didn't exclude any new models. It's just the same models that Hera did exclude. So there was nothing. It's just also we were able to put the first evidence for the heated IgM. So MWA was the first one as a specular redshift. And yeah, just to end, we could improve the result by applying a kernel density function in the foregrounds to make sure that we could improve the result by getting rid of some other anomalies in the foreground. And by doing that, we found that we could decrease the power from 30 to 23. That's it. I will just leave you with a conclusion. Thank you.
Thanks a lot for the talk. Time for quick questions.
Very nice results. So maybe you can go back to this results slide where you compared your final power spectrum also, I think, to the thermal noise.
Yeah, I think is this one?
No, I think results. Yeah, this one. Yeah. So okay. I'm trying to understand because at some points you have a thermal, what you call thermal 2 sigma. Now I presume that is the noise on the noise, the 2 sigma of the noise on the noise, right? So not the thermal noise itself. but then your results go below that, whereas all the other results, they sort of either graze it, which of course, I mean, they should. You should never go below the thermal noise or the error on the thermal noise. So I don't fully understand why at many points your results actually dive below the noise error. Why is that?
You mean the orange line at
yeah,
low?
the sort of purple line, I think, is your limit, right? But the green line, you should not go below that, right?
Yeah, no, the purple line is not actually, it's just a sample to sigma, is a sample variance, whereas the orange line is actually the limit line.
Ah, okay, then I misunderstood. Okay, I thought
Yeah.
the purple line is the result. Okay, then my
Mm.
question has been answered. Thanks.
Yeah.
Any other questions? Yes. It's a question.
Excellent result. I was actually interested about the last slide where you were mentioning KD. I guess this is some kind of interpolation scheme to solve the issue of the missing channel. No. No, that you show that
really.
you had better permit with it.
Yeah, it's not. Sorry. Yeah, it's not to solve the missing channels actually. It's just because when we are averaging in the power spectrum space where your grids are visibility, so instead of just averaging through, all the visibilities, I'm just trying to fit a KDE kernel. So as you can see here, I didn't have time to explain. So this is imaginary and real part. So the red one, the red line is the imaginary part of the visibility, and the black line is a real part of the visibility. And the two lines are the straight smooth line are fitted across the real and imaginary part. But instead of, we are just trying to get rid of this visibility to fit the foreground better, so that we are not kind of including foregrounds that are not constrained. So we're just trying to constrain the foreground well so that it doesn't leak in the EOR window when we are gridding the visibility in the Fourier space.
All right. I think we are at time now, a little overhead. So thanks, Ridhima, once again for a nice talk. And let's thank all the speakers of this session.